Okay. So last class we do the this is the final exercise we do we have done in last class, and this is just apply hydrostatic equation to compute the pressure we have in the flowing fluid. Okay, so the next exercise also we wondering to do manometer analysis. So, but in here, I don't apply the hydrostatic equation step by step, because one idea I would like to emphasize is as we know, we have the pressure will increase. Okay, the pressure will increase when the elevation, maybe I use the Z, will decrease, right? That indicates we are moving to the deeper part, but the pressure will increase. So in other words, if the pressure decrease, that indicates that we have the elevation increase. Okay, so when we go hiking on the mountain area, we actually know the ambient pressure will decrease when elevation increase. Okay. So the questions is quite simple idea. We just based on this idea and apply to these questions. So we go back to see the questions. We wondering to measure the point here. So, and this is a tank, and we wondering to know how large the pressure inside the tank. And we know inside the tank, the liquid is the oil. Okay, and we know that the oil, the gamma oil is the gamma W multiply Sg, right? Because in the questions we didn't know actually values of the oil for specific weight, but we actually know how large the S we have. So we have the specific gravity 0.8. So we actually know how to compute the oil specific specific weight. So this is under the room condition. So we actually know it's a 9,810 newtons per meter cubic, and the multiply Sg is 0.8. So we have the gamma oil. We can convert by these values. So the gamma oils is equal to 7,848 Newton meter cubic. Okay, and how other fluid we have? The second we have the fluid also include the airs. Okay, and another manometer fluid is the mercury. Okay. So we just write down if the gamma air, if we forgot how large the gamma airs, but we remember the density of the air is equal to around to 1.2 kilogram and a meter cubic, right? And we can multiply the gravity constants 9.81 and meter per second square. And you can compute how large the gamma for air we have here. Okay, I just used calculator to compute around the 1.77 and Newton per meter cubic. Okay, as we mentioned before, the gamma air is quite smaller compared to other liquid. So sometimes when we meet the problem include the air, we just neglect the contributions from the air. But in here, I just keep the air and try to compute how large the influence by the air. And we and the manometer fluid is the mercury, and I just provide the gamma for the mercury for your reference. So I can write down it's 133 and 0.000 Newton per meter cubic. Okay, and the reason why I just summarize all the specific weight for all fluid included in our problem, because we know that the hydrostatic equation, we would like to apply the gamma multiply the length, and it will convert to the pressure. Okay, but I don't step by step, because right now I know my starting point here is 1, and I can move to down here, and I maybe use the A point in here, and this point I use the B point, and this point I use the C point, and then finally I go back to the point 2 here. Okay, so I actually know going down and the pressure increase, and then going up the pressure decrease. So I start from the 1 point. So the P1 pressures, because right now I'm moving to 8, right? The direction is going down, so the pressure will increase. So I use the gamma M and multiply L3, right? Because going down and the pressure will increase. And because the point B here has the same elevation, so I didn't change the pressure. But from B to C is going up, and with the length is L2. Okay, but right now the fluid is the air. Okay, so the next, because it's going up, so I need to use the minus, because the going up the pressure will decrease, and the liquid, the fluid here is the air, and the length is the L2. Okay, so right now the pressure, I'm going to move to the point here, and finally I need to move back, going down to the 2 point here. Okay, so again, because right now we are going down, so we have the pressure is increased, and here the liquid is the oil. So I use the plus and the oil and multiply the L1, and then we're equal to the P2. And then we're equal to the P2. So here I just apply the hydrostatic equation, but I don't do the balance step by step. I just consider the main idea: going down, pressure increase; going up, pressure decrease. And I just consider what the fluid I have along the path. Okay, so just put all the numbers inside the equation. So you actually know the P2 will equal to, and the P1 is the gauge pressure 0, so we don't have the P1 values here. And so the gamma M is the 133 and 0.000 Newton per meter cubic multiply L3. L3 is here, so it's equal to 0.8 meter minus the 1.77 Newton per meter cubic, and the L2 we have here is 1 meter, and plus the gamma oil. The gamma oil is the 7.848 Newton per meter cubic, and the length is L1 here, 0.4 meter. Okay, so you can do very quickly to compute the final answers. So I check from my calculator, and plus the 7.848 multiply 0.4 meter. So the number is 109, maybe 0.5 kilo per. And we always do the pressure analysis just based on the gauge pressure. So the final answer is the gauge pressure we have. Okay, so the number maybe a little bit different compared to the answer I write down in the right corner, but It's just some gravity number. Maybe I use the different, not the 9.81. Okay, so that's a idea. If we see increase elevation, so the pressure will decrease, and we decrease the elevation and the pressure will increase. Okay, so in the following, you just consider the main idea here. Okay, you don't need to step by step to do the hydrostatic equations. Okay, so this is our final exercise for the manometers analyzed. And the next one, the different ideas is we wondering to consider our problem in focus on the flowing fluid located on the inclined pipe. So you can see the exercise here. This is the inclined pipe, and the flow will start from the point 1 flow to the point 2. So there is some pressure difference between the point 1 and point 2, and the fluid will start to flow. Okay, and we also put the manometer fluid here, and we can see actually the deflection height delta H we have. So we're wondering to derive the equation again. So just based on hydrostatic, so the P1 is our starting point, right? And then from the P1 we are going to down and to here. Okay, we will first going down and in here, right? So, and right now the liquid is the gamma A in here, and the manometer fluid is the gamma B in here. So the first we are going down, so P1 should be plus, and the liquid here is the gamma A. So the plus the gamma A, and the elevation changes is the delta Y plus the delta H, right? Because here we have the delta H, Y, and the delta H here, and we are trying to going down and at this point. And then we move to the right hand side in here, and we should going up again. Okay, so going up, we should have the minus pressures, and the fluid right now is the gamma B. Okay, because this portion is contributed by the gamma B. So the minus the gamma B, and because going up, so minus gamma B delta H. Okay, and we wondering from this point and going back to the point 2 here. So the final one still the going up, but the fluid is the fluid in here is the gamma A. So again going up, so we should have the minus, and the fluid is the gamma A. And how elevation changed, we start from here is delta Y, and plus the D2 minus D1. Okay, plus D2 minus D1. So the elevation change is delta Y, and plus the D2 minus the Z1. And then finally we are going back to the point 2. Okay, so just down elevations increase the pressure. So we have the positive here, but if we are going up, so the pressure will decrease, so we will have a negative sign in here. So we expand the equations, the P1 plus the gamma A delta Y plus the gamma A delta H, and minus the gamma B delta H, and minus the gamma A delta Y, minus the gamma A delta Z, plus the gamma A delta Z1, Z2 D1, and equal to the P2. So you can figure out some item can be cancelled out. The first one, the gamma A delta Y minus the gamma A delta Y. And we put the same point together. So we know that I put the point 1, the P1, and there is the gamma A Z1, right? So the P1 I just merge together with the Z1. Okay, so this is our piezometric pressure flow at the point 1. And I combine again the P2. The P2 here on the right hand side, I move to the left. So here we will have the minus the P2, and there is the elevation for the Z2. So I merge the Z2 with the P2. So there is the plus the gamma A Z2, and I move all other parameters to the right hand side. So we have the delta H and gamma B minus the gamma A. Okay, so this is our first equations. Okay, and the meaning is, if you're wondering to know how the piezometric pressure difference, okay, piezometric pressure difference between the 1 to 0.2, as we know, the fluid is flowing, so there is the pressure difference between the 0.1 and 0.2. So the equation showing here, we have the piezometric pressure 1 at the 0.1 minus the piezometric pressure at the 0.2 will equal to the diffraction height and multiply the specific weight difference. Okay. In other words, I can divide the both sides with the gamma A. So here I decide P1 and the gamma A Z1, and I divided the gamma A and the minus the P2 plus the gamma A Z2, and I divided the gamma A will equal to the delta H gamma B divided the gamma A and the minus 1. And the part in here, we call that the piezometric head, right? It's a piezometric head. Okay, so we can also say that the piezometric head is equal to the diffraction height multiply the specific weight ratio minus 1. Okay, so this is a very good example when we take a look and we know that the certain condition the fluid is flowing start from the 0.1 to the 0.2, and there should be the pressure difference between the 1 to 2, and that's the reason why the fluid will flow. Okay, but we only observe the diffraction height in here. How can we know how large the pressure difference between the 1 and 2 point? So we just based on the equation we derive here, we have a diffraction height, and if we know a specific weight for the fluid B and the fluid A, and then we can compute the piezometric pressure difference between the 0.1 and 0.2. Okay, so remember, keep in mind, the gamma B is our manometer fluid, and the gamma A is flowing fluid. So the difference, you should know what is your manometer fluid and what is your flowing fluid. If you know the specific weight of material, and you can compute the piezometric pressure difference between the 0.1 and the 0.2. Okay, so keep in mind, and later we have the exercise. So that we need the exercise, we put the manometer fluid here, the fluid it B is the mercury. Okay, so we should know how large the mercury we have, the gamma n. It's our manometer specific weight. And the questions I already provided the number in here because we wondering to use the imperial unit. So I guess you don't know how large the mercury specific weight for imperial unit. So I write down in here. So we know that the gamma n is equal to the A47 and the bomb force divided the foot cubic. Okay, and right now the flowing fluid A, we right now it is the water liquid. So we know that the water liquid, the gamma W will equal to the 62.4 and also the bomb force divided the Ft cubic. Okay, so what's the questions? We only know the diffraction height in here. We have a diffraction height. We actually know the number here is delta H is 1 inch. But we consider our unit is the Ft. So the first one, we should convert the diffraction height 1 inch to be the Ft. So the 12 over 1 Ft, right? Because we know that the 1 Ft is equal to 12 inches. So just convert the unit we want. Okay? And the question we should require to answer is how large the piezometric pressure difference and what is the piezometric height between the 0.1 and 0.2. Okay, so maybe we try to answer the piezometric pressure difference between the 0.1 and 0.2, and the second we wondering to know how large the height difference between the 0.1 and 0.2. Okay, so as you remember, for answer the question 1, the piezometric pressure difference between the 0.8 and 0.1, we actually know the piezometric pressure difference between the 0.1 and 0.2 will equal to the diffraction height, right? Multiply the gamma B minus the gamma A. And we know that the gamma B is our manometer fluid. So I replace the B to mercury specific weight. And the flowing fluid is right now the water. So I use the gamma W. So all the number we have, so we can put the number inside the equations. So we have 12 over 1 Ft and multiply the gamma n is A47 bomb force divided the Ft cubic minus the 62.4 and the bomb force multiply the Ft cubic. And you can calculate the answer very quickly. You just based on these equations divided the 12. So the answer is about the 65.4, and because right now our unit is the PSF, so I directly use the PSF. So this is the answer for the question 1. So that means if we in the following class in the future you have the problem like this, you don't need to apply the hydrostatic equation step by step, because you already know if we wondering to measure the piezometric pressure difference, it's just based on the diffraction height we have here, and what is your manometer fluid, and what is your flowing fluid. And you only need the gamma A and the gamma B and the diffraction height, and you can compute the pressure difference very quickly. At 82 points, you can calculate. Okay? So that the question is, if we wondering to measure the pressure difference, you just put the pressure tape if we want to measure the point 1 to point 2, so you just put the pressure taps on the location you want. And then you can just observe the diffraction height you have, and then you can compute the pressure difference very quickly. Okay, so the question 2 is quite simple because we already know the piezometric pressure difference P delta Z. And we just divided the gamma A, and then we can convert the answer to the head difference. Okay, the head difference. So we have the value in here is 65.4, and the PSF divided the gamma A right now is the water. So we just divided 62.4, and the unit is the bound force divided Ft cubed. So finally, you know that the answer, you just keep to compute the header difference, okay? It's around 1.05, and the unit is the length, okay? Because we are compute the head, okay? The head difference. So again, I wondering to emphasize the idea. If you wondering to measure the pressure difference between the point 2 and point 1, you just put the pressure, the taps in here, and the pressure tap in here, and then you will observe the diffraction height difference, and you can compute just based on the equation showing here. You can compute the pressure difference between any 2 points. So you just depend on where you put the tap and where is the location, and then you can measure the pressure difference very quickly. Okay, so this is just the final exercise related to the hydrostatic equations. And then the next topic, we wondering to move the difference topic. So before that, I just put the one slide, just do quick summary. Previous all the exercise, we just based on 2 assumptions, and then we can deal the problem. So the first assumption, we always consider the constant fluid density. Okay, we consider the constant fluid density, and the condition is just based on hydrostatic. And then we have the 2 manometer equations. The first one, we call that the gauge pressure analysis. So you don't need apply the hydrostatic equation step by step. You just consider when elevation down and you have the positive pressure increase, okay? When the elevation up and you have the negative, the pressure decrease, okay? Just based on the gauge pressure ideas, okay? And the second equations, we have the differential pressure analysis. So we wondering, our purpose is wondering to measure any 2 points, the pressure difference between 2 points. So you just observe how large the diffraction height you have, and then you need to know what your manometer fluid gamma B, and what is your flowing fluid gamma A, and then you can compute the pressure difference very quickly. But right now the equation is just for the piezometric head difference we have. Okay, so that if you forgot some importance, but you should keep in mind some idea based on this slide. Just 2 important equations we will apply in the features, just based on the constant density fluid assumptions, and the second condition is hydrostatic. Okay, so but the modern development, the device to measure the pressures, we based on the one famous material, we call that the piezoelectric material. So this material is very sensitive to the ambient pressure changes, will induce the voltage changes. So the piezoelectric material will sensitive to the voltage changes caused by the pressure difference. And in case we can put the individual independent measurement for the traditional methods. So the traditional method, we can measure pressures based on the liquid height difference, so we can know how large the pressure we have. And we will do some relationship analysis, regression line, between the pressure units caused by the voltage changes, and do some linear relationship between the height. Okay, so in the following applications, when we know how voltage changes, we can, based on the equation here, convert how large the pressure we have. Okay, so this is a very modern device. When we measure the environment pressure, we will use the piezoelastic material. So we call that is pressure transducers. Okay, the pressure transducers. So right now we move the topic to the pressure distribution problems. Okay, so this slide just show a special case. We consider a flat surface panel, and we consider right now the pressures is uniform pressure distributions. So what's the problem we would like to emphasize here? When we meet some problems, we wondering to know how large the pressure force we have. How large the pressure force we have, and what is the locations of the pressure. Okay, the left hand side, the figure show the distribution of the pressures is uniform, and we wondering to change to the right hand side. So we wondering to know what is the pressure force, the net of the pressure force we have. And if we have the pressure force, where is the locations for the pressure force? So we need to find out the centers of the pressure force. So because of the uniform pressure distribution, so we actually know the center of the plate is our center of the pressure force. Okay, because the plate maybe is the symmetry shape. So the center is the location for the pressure force. And what the pressure force we will have? So we do the integration problems because we know the FP will integrate all the areas, and we have the pressure in here. Okay, we have the pressure in here. So we assume our pressure is the P, and multiply the small areas, the A, and integrate all the possible force caused by the different pressures. But right now we have the unit factors is the N. N is the normal factors of the surface. So as we know, the pressure force directions is always have the opposite directions compared to the normal factors. Okay, so we have the additional minus sign in here because the pressure force factor directions is always opposite directions compared to the normal factor of the surface. And then, as we know, the pressures right now here is uniform, so didn't change with the locations. So we can put the P outside the equation integration, and inside we only have the minus the normal factors of the surface and integrate all the areas. So finally, we know that the answer is minus P multiply the total area with the normal factor opposite directions. Okay, so this is the pressure force we will have if we consider the plate is flat plate panel, and the pressure is uniform pressure distributions. Okay, so this is just an idea we would like to emphasize when we deal the problem with the pressure distribution. So only two parameters are critical. The one is what is the magnitude of your net pressure force. The second is the location, or where is the location of your pressure force. So you should find out the two parameters, and then you can solve some problems based on this idea. Okay, so another rule I would like to emphasize here, if you based on this idea, so I write down the sentence here, we call that is the gauge pressure rule. So the condition is when a uniform atmosphere pressure acts on a body, and you can integrate this pressure over all the area, and finally we know that the net pressure force is equal to 0. So that you put some body in environment conditions, and then you can see we have a different pressure distribution along the body boundaries. And then if you compute the integration for all the pressures we have, and finally will equal to 0. Okay, so that we call that is the gauge pressure rule. Because why? The reason usually we consider the problems just based on the gauge pressures. Because the gauge pressure always the sum of the all contribution force caused by the different pressure will equal 0. Okay, so that we call that is the gauge pressure rule. So we emphasize when you have the pressure problems, you just consider the gauge pressure. Because based on the gauge pressure rule, we know that the contribution force integrate all the pressure distribution around our body will equal 0. Okay, so but in real case, if we put the panel into the waters, you can see the pressure is not uniform, right? So this is our two conditions. If we put the plate into the water, you cannot have the uniform pressure distribution. Because we know if we go into the deeper part, the pressure will increase. So this is the two cases when we have the problem. We put the panel into the water, and the critical information we still focus on two parameters. The first one is the pressure force, how large magnitudes of the pressure force we have. And the second, we wanting to know where is the center of the pressure. And because the shape of the panel we usually consider is the symmetry. So we have the center is, we call that the centroid point. The center of the panel, we call that the centroid point. So totally, we should understand how large the pressure force we have. And in that case, we call that is the hydrostatic pressure force. Because the pressure distribution just based on the hydrostatic conditions. So we're going down and the pressure will increase. And sometimes we call that the center of the pressure is the CP point. Okay, it's the CP point. So in the next class, we will introduce how can we know the FP magnitude and how can we determine the CP locations. But the bottom sentence already highlight the idea how can we know, because the center of the pressure here is calculate the top due to the pressure force is same as the torque due to the pressure distribution. So in the next class, I will base on this idea. So we deal the problem with the moment balance, and we know that the moment balance one is caused by the FP in here, and we have the center point, center of the pressure point, and will equal to the moment caused by all the pressure distributions. So the moment should be balanced, and then the panel will stand there, right? If the moment is not balanced, the panel will rotate. But right now you put the panel in there, so you see the panel didn't moving. Okay, so that means the moment is the balance under this condition. So we may the time is it's over, so we may have a break, and in the next class I will teach you how to determine the FP values and how can we determine the location of the CP. Okay.